Okay, we're going to continue on. We're off to chapter 9 here today. So we're going to talk about sort of stoichiometry. So in some previous chapters, we talked about converting grams to moles. We talked about obviously balancing equations and different types of reactions. In the previous sort of chapter we covered. So we're going to kind of put both of those things together. We're going to use balanced equations and how much we start with to predict how much product we should produce or how much reactants we should start with, which is really stoichiometry. So let us get into it here. So when we look at a balanced equation, there's several relationships that we can actually get from the balanced equation. Just really a lot of them by looking just at the coefficients. For example, here we could say that there are two molecules of H2 react with one molecule of O2 to produce a couple molecules there of H2O. The one that we really will be using here in this chapter and what you use in stoichiometry really is sort of the middle relationship here. And that is what is sometimes referred to mole-to-mole relationship. And the mole-to-mole relationship is pretty much found simply by just taking the coefficients in the balanced equation. So when we do stoichiometry type problems, it's really important to always make sure that your equation is balanced. Otherwise, all your calculations are going to be off. So we could say that there are 2 moles of H2 react with 1 mole of O2 to produce 2 moles of H2O. They are sort of like proportion of what you need to kind of throw into that reaction to sort of produce a certain amount of product. But they are simply just the coefficients. Sometimes people sort of wonder like where we get all the kind of relationships from. And it is just simply as taking the number that's there in the balanced equation. The last relationship we really won't use too much, but it is the conservation of mass. Obviously, as we talked about when we were balancing equations, if you started with like 4 carbons on the left, you should end up with 4 carbons on the right. They may be in different compounds, but since carbon is like 12 grams or so, on the left is 12 grams on the right. So we end up with really the same mass of elements on each side of a reaction. So stoichiometry is really nothing more than conversion factors. And it's kind of the difference is where we get the conversion factor from. So instead of going to a table and looking up like 12 inches is a foot, we actually get the conversion factor from the balanced equation. And the reason we oftentimes have to do that is because in the problem that we're given something in the actual reaction that we're really not interested in, but we're interested in something else in the actual equation. And we need a way to go from, say, a reactant to a product to a reactant, or even a reactant to a reactant, or a product to a product. We need some type of conversion factor to allow us to kind of go from one thing in the reaction to something else. And that's really where the stoichiometry part of it comes into play. We could do a lot of sort of calculations involved in stoichiometry, including like the lab we did the other week there with the yellow. We could do calculations to predict, based on, I think we started there with some potassium iodide, how much we started with. We can do a calculation to figure out, in theory, how much we should produce in that reaction of the product. We could also go the other way around and if we know how much product we produce in a particular reaction, we can sort of back calculate and figure out how much reactants we actually kind of threw in there to get that much products to come out. So when we do stoichiometry problem, the units can really be, any type of unit, but ultimately the goal and pretty much the first step that you kind of want to do in most stoichiometry problems is to kind of get everybody into moles. So moles is sort of our common unit that we use, obviously, in stoichiometry. So we've talked about previously, right, to get into moles, a lot of times we measure things out in grams, right, and we need to go to moles. And that is the molar mass, right, that we could get from the periodic table that allows us to kind of do that conversion. So that conversion that we did earlier in an earlier chapter there, we use a lot in stoichiometry, going from grams to moles, just like you did in your experiment. You weighed out a certain amount of grams, right, of whatever you were starting with, and you'll need to kind of convert that into moles as you go through the stoichiometry step. Later on, sometimes concentration like molarity, which we'll talk about in a later chapter, and volume is used to get the moles. So there's a lot of different units that we can use, but really the whole sort of process of stoichiometry pretty much all revolves around basically moles. And that's sort of the mole method is sometimes referred to. And we get what is sometimes referred to as being stoichiometrically equal to each other, this relationship from the balanced equation. So when we look at these steps that involve stoichiometry, there's several steps that really come down. And up here, there's a few more steps listed, but for the most part, basic stoichiometry problems will basically have 4 basic steps. And that is, you want to balance the equation, you want to convert to moles, you want to do the mole to mole relationship, and you then want to convert to some other unit. So, basically, that's really the first step there. Make sure you have a balanced equation. If you happen to give everything in words, you obviously need to write the correct formulas down and then balance it. And then the next thing you want to do is convert whatever they give you basically to moles. And again, a lot of times that is going from grams to moles. So you're going to use that molar mass to do that. The next thing is really the stoichiometry part, which is go to the balanced equation there and find the mole to mole relationship. What you're looking for when you go to the equation is the 2 things that you're interested in is whatever they give you. The other thing that you're interested in the equation is what you're trying to find. So for example, if you're trying to find how much product, that would be the other thing that you would be interested in. And then the last step really that you sometimes do and you don't do is trying to convert the moles into some other unit. So when you're done with sort of step number 3 there, the stoichiometry step, you will always be in units of moles. But a lot of times we want to know how many grams we would produce or something like that. So on the back end of a lot of things, you then need to kind of use the molar mass again in a lot of cases to convert moles back to. These are the 4 basic steps, no matter how sort of confusing the problem may be. Kind of balance the equation, convert to moles, mole to mole relationship, and then convert those moles into some other unit. Now, if some step is done for you, don't go backwards. I've seen people do it a lot. They unconvert things and then reconvert it. So if something is converted to moles for you to begin with, you don't need to unconvert it, then convert it back to moles. So you just kind of continue on to the next step. So let's talk about what we can get from an equation. So if we have an equation like this, we could get several relationships, stoichiometric relationships. And again, we could look at this and say for every 2 moles of CO that we toss in there, we need to toss in there 1 mole of O2. And those numbers are coming from the coefficients in the balanced equation. We could also say that for every 2 moles of CO we put in there, we will produce 2 moles of CO2. We could also see that for every 1 mole of O2 we put in there, we get 2 moles of CO2. And again, these are all just coming straight from the balanced equation. These are what I refer to as, like I said, being stoichiometrically equal to each other. They are not equal in terms of number. Obviously, 1 does not equal 2, but they are equal to each other in terms of proportion of what you need to dump into this reaction to sort of produce the amount of product that you would want. Kind of like when you bake cookies, right? You need to throw so much flour, so much chocolate chips, all that stuff to get a dozen cookies out. Same idea here. You got to toss a couple moles of the CO with 1 mole of the O2, and you get some CO2 out. Now, because these are technically equalities and equal to each other, just like any other type of conversion equality, we could write 2 conversion factors for each of these. For example, for the first one, we could say that there are 2 moles of CO over 1 mole of O2, or we could use the opposite of it, 1 mole of O2 over 2 moles of CO. For the second one there, we could say that there are 2 moles of CO over 2 moles of CO2. Or obviously the reverse, 2 moles of CO2 over 2 moles of CO. And lastly, we could, for the last relationship there, 1 mole of O2 over 2 moles of CO2 are 2 moles of CO2 over 1 mole of O2 here. So from this one equation, we have basically three equivalents, and we have 6 different conversion factors that we could use in a problem. Much like a normal conversion factor, you don't use them all. You obviously would use the one that is correct. And just like dimensional analysis, its opposites cancel. So, you know, if we were starting with, for example, if we started with 10 moles of CO2 were produced, and we wanted to know how many moles of O2 did we start with, we could start with the balanced equation, which is here. So that's the first step. Whatever they gave us, it's already converted to moles. That's like the second step. So we don't actually have to do it in this case. So the third step, which is the stoichiometry step, would be we would take our 10 moles of CO2 that we produced, and we're interested in O2. So we want that relationship between these two guys, which we already saw down here. And obviously from that one, we have these 2 conversion factors that we could use. Now, in this particular case, we should use the one on the left or the one on the right. We want to get rid of CO2, which means the CO2 needs to go on the bottom. So we would want to use the one here on the left as our conversion factor. And this is the big stoichiometry step. Don't close your eyes, you'll miss it. And this is 2 moles of CO2. Here, the moles of CO2, which we're really not interested in. We're interested again in how many moles of O2 that we started with. I'm going to do it without the calculator there. I'm going to go with 5. That sounds like a good number. Moles of O2. That's okay. And this would technically be the third step. And what that really tells us is if we wanted to produce 10 moles of CO2 in this reaction, we would have to dump in there 5 moles of O2. And if we wanted to know how many grams that would be, we could do the fourth step. We would need the molar mass here of O2 to do that, which I believe is 32 grams per mole. And we could go 32 grams per mole of O2. And that will get us about 160 grams of O2 would be necessary here. So again, what this calculation would mean is you would need to dump in there 160 grams of O2 in this reaction. If everything went perfect, you should produce 10 moles of CO2 in this case. And again, these are the 4 basic steps: balance equation, convert to moles, do the mole to mole relationship, and convert out of moles in that step. Any questions on that? Yeah. It's just simply the relationship of the coefficients in the balance equation, and it's actually just the numbers. So when we look at the numbers in the balanced equation, these could be thought of as moles of each of those things. And so what that means is, for example, the first guy here, that would be 2 moles of CO would be equal to 1 mole of O2. So it's basically, again, they're not equal in terms of numbers, you know, but they're equal in terms of proportions that you need to put in there for the reaction to take place. So it actually just comes simply from the balanced equation, the coefficients, those relationships. And that's again where we got this guy as well. 1 mole of O2 gives us 2 moles of CO2 from the coefficient. And that's why it is really, really important when you do these type of problems that you always make sure that the equation is balanced, because if it is not, your whole calculation is pretty much going to be wrong. So like before, if you see an equation, there's numbers in the coefficients, probably going to be balanced. You might want to check it. But definitely if you have an equation, there's like no coefficient numbers or anything, you should definitely take a good look at it and make sure that it is balanced. And if not, you should definitely make sure you balance it. Other questions on that? So this is the basics of stoichiometry, which hopefully you can see here is really just a conversion factor. And like I said, it's just a different place that you get the conversion factor from. It actually always will come from the balanced equation. It's not like you go find it in a table. It is. That's the molar mass of O2 from the periodic table. Oxygen 16 times 2. Gets you 32. Yep. Over 1 mole of O2, right? Molar mass is grams per mole, right? When you calculate it from the periodic table. Other questions? Okay. That's what we just talked about. So why don't we try one here? Let's do just the first part here. We'll come back to the second part. All right, lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed from the complete reaction of 5.32 moles of lithium with water? So we'll go through this one together, this first part here. So the first thing you always want to do is get to the balanced equation. And in this case, we are not given the equation, but we're given everything in words. So as we talked about with equations, we want to start with the correct formulas. So lithium metal is just lithium by itself uncombined. Reacts with water, which is H2O. And to form means on the other side of the arrow, hydrogen gas, which again, you want to remember is a diatomic molecule. So that's an H2 action going on there. And some lithium hydroxide, which is LiOH. So again, here, I am not balancing the equation as we talked about when we were doing equations. I'm just making sure I first get down all the correct formulas. Now I should go back and make sure it's balanced. It is not balanced in this case, so we do have to do a little bit of balancing here. And I'm just going to throw some 2's down. And maybe there. I just wrote 2's. How did I do? There's 2 lithiums, 4 hydrogens, and 2 oxygens. I think we're good in that case. So this pretty much in every stoichiometry step problem that you do is always really the first step that you want to do. The second step that you typically want to do is take whatever they gave us. So in this case, the only thing that they gave us was the 5.32 moles of lithium. Now, the second step in stoichiometry is to take whatever they gave you and convert it to moles. Do I need to do that in this case? I do not. It's already done for us. So that second step, again, is already done for us. The third step is the stoichiometry step. So in the third step, what we want to do is now go to our balanced equation and find the 2 things we're interested in. The first thing we're interested in is whatever they gave us, which is lithium. So here is our lithium. The other thing that we're interested in is what we are trying to find. So in this case, we are trying to find how many moles of H2. So from the equation, we could get our relationship, and that is for every 2 moles of lithium I throw in there, I get 1 mole of H2 out. And again, simply just the coefficients from the balanced equation. That technically gives me 2 conversion factors. It gives me 2 moles of lithium over 1 mole of H2, or the opposite, 1 mole of H2 over 2 moles of lithium. So now that we got our sort of conversion factors, we're ready to do the third step. So we're going to start with our 5.32 moles of lithium. And which conversion factor should I use here? One on the left or the one on the right? The one on the right, because the goal here is to get rid of lithium, which is what we're not interested in, and basically end up with hydrogen. So we do want to use the one on the right here, because again, opposites will cancel. That gives us 1 mole of H2, 2 moles of lithium, and I will grab the calculator here. 5.32 divided by 2 gives me 2.66 moles of hydrogen in this case. And in this particular problem, that is actually the answer, because we're looking for how many moles. So we actually only needed to go to sort of the third step here, which is how many moles. If we wanted to know grams, we could do one additional step, right? We could use the molar mass of H2 at this point and convert the moles into grams, and we would know how many grams. First off, any questions on the calculation part? Yeah. So when we get to the third step, it's really the stoichiometry part of the calculation. And what we're looking for is what's referred to as the mole-to-mole relationship between the two things we're interested in. And in this particular problem, we were given lithium. So that obviously is one thing we're interested in. The other thing you're interested in typically is what you're trying to find, which is hydrogen. So those are the two things. So we need to go to the equation to find that mole-to-mole relationship, which is just the coefficients. Other questions? So again, what this calculation basically is telling you is in this particular reaction, if you dumped in there 5.32 moles of lithium, and again, everything went perfect, nothing went wrong, you didn't spill anything, no side reactions, you would, in theory, produce 2.66 moles of hydrogen. And this is what is sometimes referred to as the theoretical yield. Like in your experiment where they ask you to calculate your theoretical yield based on how many grams of Ki you started with. Any questions on that one there? All right, so why don't we do the second part now that I scratched out? So I think I got it here somewhere again, maybe. Yeah, so okay, let's do the second part here. So I'll scratch out the first part. All right, same reaction, same stuff, but in this case, we want to know how many grams of H2 we would produce. So give it a go. Let me give you some info that will probably be helpful for you. Lithium from the periodic table, 6.941. Hydrogen, 1.008. All right, so follow those 4 steps. Balance equation. Convert to moles. Mole-to-mole relationship, and convert to other units. All right, take a few minutes, see what you come up with there. Again, if you're ever lost, just follow these steps. So we want the balanced equation here first, and obviously we're using the same equation as previous there, which was our lithium and our water, making our hydrogen gas and some lithium hydroxide. I believe there were some 2s going on here, I think. So that is always first step. Second step is to take whatever they gave us, which in this case is 81.75 grams of lithium, and convert it to moles. So obviously in this case, we do need to do that because it's in grams. We would go to the periodic table and find the molar mass there of lithium and do a conversion like we've done before, which is our second step here. Again, grams on the bottom so that they cancel, 6.941 grams per mole of lithium. The grams here cancel. And if you got an answer at this point, you are looking at, we'll call it 11.78 moles of lithium, which again is really the second step here in this process. At this point, the purpose really of why we need to convert things into moles is for really the third step, which is the mole-to-mole relationship. That way the units will always cancel out correctly and everything like that. So that is where we want to go next. Again, we are looking for the 2 things we're interested in, and it happens to be the same relationship that we saw previously. So it is the 2 moles of lithium to our 1 mole of hydrogen. Lithium to 1 mole of hydrogen. So we will have the same 2 conversion factors that we had in the previous step there, the problem. So we will do that for our third step. And again, this really is the stoichiometry part. We want to get rid of lithium. So once again, we're going to put the moles of lithium on the bottom. We're going to have the moles of hydrogen up on top. The moles of lithium at this point will cancel out. And that would get us divided by 2. Looks like a 5.89 moles of H2. And that is the really big stoichiometry part of the calculation. It is the conversion that allows us to go from lithium in this case to hydrogen. Any questions on that there? Now we're to really the fourth step, which is, again, after you do that third step, you will always be in moles. If you do it correctly, you should always be in moles. And in this case, we're not really interested in moles as our answer, but we do want grams. So very commonly here on the back end, we do have to use the molar mass to go from moles to grams. It's important to remember, and where some people sometimes make mistakes, is we are no longer with lithium at this point, right? We have now converted it to hydrogen. So we want to make sure we use the molar mass for H2 and not lithium. So again, you would go back to the periodic table there, and that would be 2 times 1.008 grams per mole for our H2, or 2.016. And that gives us 11.9 grams of hydrogen would be produced in this case. So again, what that number means is if we tossed into this reaction our 81.75 grams of lithium, everything went perfect. In theory, we should produce 11.9 grams of hydrogen gas. And again, this is what is referred to as the theoretical yield. And again, that is step number 4 here. Any questions on any of those steps? As was the question that was just asked earlier, you absolutely could do it all in one step along the way. You don't have to get an answer after each step. You can just do it as one big calculation. Normal sort of rules apply. If you are sort of getting answers after each step, try not to round too much until the end. Yeah. So, kind of take the number a good distance and then round it at the end. Or again, like I said, you could just put it all together in one sort of big calculation is fine. Any questions? Yeah.
Can you go over how you found the coefficients for like 2 lithium? It produces everything on the other side of the arrow, right?
So there's a good question. I think what your question is first off, it is just the coefficients in the balance equation. So that's where the 2 moles come from and the 1 mole for the hydrogen. But sometimes people think in terms of stoichiometry, you always have to kind of do relationships sort of across the arrow, with something on the other side. And you actually don't. You can, like we did here, have a relationship from something on the reactant side to the product side. You could also start on the product side and go across to the reactant side and have that relationship go that way. You could also stay on the reactant side. So you could do some calculation between 2 reactants. And if you had, in this case, like we do here, 2 products, you could also do a calculation using stoichiometry between the 2 products. So it doesn't always have to go across the arrow, if that's sort of your question. You could do relationship and stoichiometry calculations on the same side of the arrow. It's just a relationship between everybody in the actual equation. Yep. Exactly. So for example, if this problem was a little bit different and it said we threw in the 81.75 grams of hydrogen or lithium, how many grams of water would we need? We would do the exact same calculation, except that the relationship here would be the 2-to-2 relationship. And then obviously the molar mass would be different because it would be water at the end, but it would work exactly the same way. Yep. Other questions? All right. So now that we are professionals, let's do a few more here. Let's see. All right, let's see. I got one here somewhere. There it is. All right, why don't we try this one here? All right, if 765 grams of C6H12O6 is consumed by the body, what is the mass of CO2 produced? So how many grams of CO2 is what we're looking for? And I'll give you some numbers here. Carbon is 12.01 there on the periodic table. Hydrogen, 1.008. And oxygen is 16. All right, take a few minutes. Again, follow the same 4 steps and see what you come up with. All right, let's take a look. So again, we'll just follow the same 4 steps. So in this particular case, the first step's done for us. We have a balanced equation. Again, the second step is to convert to moles, which we do need to do since we're given 765 grams of it. So we would go to the periodic table there, 6 times 12.01 for our carbon, plus 12 times 1.008 for our hydrogens, and 6 times 16 there for our oxygen is going to give us a $180.2 grams per mole, I think. And we're going to use that to convert our grams into moles. So we will take our 765 grams of C6H12O6. We're going to have the grams on the bottom so that they cancel. And if we do that and you get an answer at this point, you are something like, looks like maybe 4.245, take it a few digits. Again, remember that really this step is to allow us to correctly do the next step, which is the stoichiometry part, and that is the third part. Again, we're going to go to the equation and find the two things we're interested in. Obviously, here we are interested in what we just converted, and we are also interested in what we are trying to find, which is the CO2. And from the equation, we can see for every 1 mole of C6H12O6 we toss in there, we get out 6 moles of CO2. Again, just simply the coefficients there for that relationship. That's going to allow us to continue with our calculation here of 4.245. Now we can do the stoichiometry part and get rid of what we're not interested in. So that means that needs to go on the bottom, which would be 1 mole of C6H12O6. Up on top would be what we are interested in, 6 moles of the CO2. The moles of those guys will cancel. Timesing this guy by 6 gets us something in the ballpark of 25.472 moles of CO2. Any questions so far? This is close to what we want, but we're in the wrong units at this point, which is very commonly happens. We're in moles, but we do want grams. So once again, we need to do one more conversion here. We need to get the molar mass here now of CO2 as we've converted to it. So that is 12.01 for the carbon, plus a couple of 16s there for our oxygens. Going to get you a 44.01 as the molar mass for CO2. So using the molar mass there, we could do the final step, which is taking our moles of CO2. Here we actually want the grams up on top, so we do end up with grams. And if we do that, 44.01, looks like we end up with 1121 grams of CO2. Or if you want to still think about sig figs at this point in our career, which you should, 1120 grams of CO2 probably would be the correct answer, as that is 3 significant figures at that point. Again, that number at the end would be the theoretical yield here of CO2. By the way, if you are talking about a theoretical yield, it does have to be a product. Otherwise, it's not a yield. So it's got to be a product there that you're talking about. Again, hopefully you can kind of see a pattern here of the 4 steps that you need to follow. And as was said earlier, you obviously could just combine all the steps together in one calculation. Any questions on any part of that there? Yeah, so really the only number that was in the entire problem was the 765, which is 3. And technically everything you do in between is multiplying and dividing. So everything in between is sort of exact numbers and those type of things. So you could look at the first number. Other questions? Okay. This, actually, you know, I'm gonna skip this one. I think we'll come back. I'll throw it through if you want to look at it there, combining the steps. Let's talk about another sort of aspect of stoichiometry, which is important, which is limiting reagents. So limiting reagents are sometimes called limiting reactants as well. When we do a particular reaction, there's usually not an equal amount, if you will, of reactants there to react with each other. And what I mean is, in most cases, there's usually one reactant that gets used up first, and there's another reactant that you got plenty of. So if you think about the experiment we kind of did the other day with the potassium iodine, we made the yellow, you weighed out like a little bit of grams of something, right? And then you dumped a whole bunch of liquid in there, right? And in terms of the limiting reagent in that experiment, it was the grams that you weighed out. Obviously, you had plenty of the liquid you dumped in there. You had way more liquid you ended up in the waste anyways, but it was the excess reagent. So we end up with 2 types of reagents or reactants. and one is the limiting reagent. And that is the one that gets used up in the reaction. And then we also have the excess reagent. And that one you have plenty of. And you have some left over when the reaction is done. So if you think about the importance of those two things is pretty much if you have, for example, just a simple A plus B comes together to make A and B. And let's say that the A here is our limiting reagent and B is our excess reagent. Once we run out of A at some point, there is really no chance of making any more product, right? Because you need both of them. You need an A and a B to kind of put together. So once that A runs out, there is really going to be no way to make more product. And the importance of that is it is always the limiting reagent that determines how much product you can make. So as soon as it's gone, there's no chance to make any product. So it's always that limiting reagent that determines how much product you make. So going back to sort of the experiment that we did the other day is really the little bit of grams that you weighed out, which is what you would want to start with to figure out how much product you would make, because again, that was the limiting reagent in that case. Any questions on that there? Okay. Now, the excess reagent, like I said, you have plenty of. You can actually figure out in calculations, as we'll talk about, how much of that excess reagent we will have left over when it's all said and done. But it's always a limiting reagent that you want to focus in on when trying to figure out, which one, how much product you will make. So if we look at let's go back. If we look at this here, we got some female exercise people and some guy exercise guys. And if we want to make exercise buddies here, we need one of each. And we could clearly see in this case, it is the guys that's the limiting reagent. As soon as we sort of run out of guys, there's no more chance of making any more product. We could also see that in order to make each of those buddies on the bottom, we need one of each of these. We could also figure out that at the end, we have two left over here of our excess reagent. In this particular case, our guys over here would be our limiting reagent. So these are common sort of things that we can sort of figure out as we do these type of problems, how much product we should produce, how much of the excess reagents left over. So how do we approach these guys? Well, we basically follow the same 4 steps that we do in a basic stoichiometry problem, but there is sort of an additional step that you have to do along the way, which is you have to do a calculation to figure out which one is the limiting reagent. Now, how do you know it is sort of a limiting reagent problem versus a kind of basic stoichiometry problem like the one we have been doing? It is based on what is given to you. If you are given enough information about the reactants that you could get to moles of each reactant, then it's definitely a limiting reagent problem. So that is definitely how you can recognize I need to find the limiting reagent. You are given enough information, whatever that information is, that you could do some conversions to get to moles of each of the reactants, then it definitely is a limiting reagent problem. If you look back at sort of the calculations we did previously, we were given really just one information about somebody, right? Not both of them or anything like that. So that is really the key, that if you have enough information to get to moles of each reactant, then it definitely is a limiting reagent problem. So if we look at this guy here, and again, we have our stoichiometry. So let's just say, for example, in this particular case, we are going to start with 4 moles of sulfur in this reaction and 20 moles of F2 we're going to start with. These are like our starting amounts. And we want to basically try to figure out which one is the limiting reagent in this case. So the steps to do it will be very similar to what we did before. Everything, even limiting reagent problem, still starts with the same step, which is make sure you got a balanced equation. The second step is still the same. It happened to be done for us here is convert whatever they gave us into moles. So again, obviously here we would use the molar mass if it wasn't in moles and convert it to moles. But now we have the moles of each one. The additional step comes right at this point. We want to do a calculation to figure out which one's the limiting reagent. Again, we have the starting amounts of both reactants. So that definitely tells us we have a limiting reagent type situation happening. So we're going to do just a basic calculation that basically says you could choose either reactant to do this calculation. I'm going to choose sulfur. And what I'm going to try to figure out is if I want to use up all my sulfur, how much fluorine would I need? So this is the sort of limiting reagent calculation that we're going to do here. And we will do it just like normal. So I'm going to take the starting amount of my sulfur, which is 4 moles. I'm going to do just a basic stoichiometry calculation going to the equation. I see, as it says up here, for every 1 mole of sulfur, I am getting in there 3 moles of F2. So kind of the same idea as what we did before. We're going to get rid of the sulfur. So 1 mole of sulfur on the bottom, 3 moles of F2 up on top. The moles of sulfur will cancel. And I believe that is 12 moles of F2 is needed. So just so we're clear, the calculation I'm doing right now is really not a calculation to figure out how much product or anything like that. It's simply just a little calculation here to figure out which one is the limiting reagent. Any questions so far on that calculation? Now, here's the important part. You need to then take that number. I need 12 moles of F2. I want to go up and look at how many moles of F2 I am starting with. I am starting with 20 moles of F2, and I only need 12 moles. Do I have enough? I do. And because I do have enough, what that tells me is the F2 is the excess reagent, because you got enough. And by default, what that would mean is the S is our limiting reagent. Any question on that calculation? Now, like I said, you could actually choose either one. So I'm going to do the opposite calculation just to show you that it comes out the same way, not in terms of numbers, but in terms of what it tells you. So let's just say we did the opposite and you decided I want to figure out how much sulfur is needed to use up all the F2. I would start with my moles of fluorine. I would use the same relationship from the equation, obviously reversed here since we're doing the opposite calculation. And 1 mole of sulfur gives me 20 divided by 3. Gives me 6.7 moles of sulfur would be needed to use up all of the fluorine. So in this case, what I would be comparing is the moles of sulfur to the moles of sulfur I started with. I need 6.7. I started with 4. Do I have enough? I do not. What that means is exactly what the other thing told us. The sulfur is the limiting reagent and the fluorine is the excess reagent. You absolutely do not have to do both calculations. You could choose either one. I'm just showing you could choose either one and they'll tell you the same thing. Any questions on that there? So this is important because now I know in this particular case that sulfur is the limiting reagent. And if I want to know how much product I'm going to make, I should do it using sulfur in this case. The important part, though, is when you actually go back and now do the actual calculation, you want to make sure you go back and use the actual starting amount for your limiting reagent, not any numbers that are down here or anything like that. You want to use the starting amount for the actual calculation. So if I were to do this, I would then go with my 4 moles of sulfur because it's the limiting reagent. I would do the mole-to-mole relationship between sulfur and our product. and it would tell me I would produce 4 moles of SF6. This would be my theoretical yield in moles, which I could, if I wanted to, convert to grams using the molar mass as well, which would give me my theoretical yield in grams. So it really is the same 4 steps that you need to do for a basic stoichiometry problem. You need to insert a small little calculation to figure out, which one is the limiting reagent, and you want to make sure you use the limiting reagent starting amount to figure out the product. First off, any questions on that there? Now, we talked about earlier that a very common question is how much excess reagent would be left over. From my calculation, I could actually figure that out as well. I already figured out that I needed 12 moles of my F2, and I'm starting with 20 moles of it. How much F2 would be left over in moles? It would be how much I started with, which was 20, minus how much I needed, which was 12, which tells me I got 8 moles of F2 left over in this reaction. And again, you could use that little limiting reagent calculation to help you figure out how much of the excess reagent would be left over. And same idea, I could just convert that to grams if I want to know how many grams that would be. So those are common sort of questions that are asked here in a limiting reagent situation. Any questions on that there? Yeah. So earlier on, I happened to choose this to figure out limiting reagent, but what this really told me was that if I want to use up all my sulfur, which is actually what happens in this reaction because sulfur is a limiting reagent, I would need to put in there 12 moles of the fluorine, right? I started with 20 moles of the fluorine. So it's just simply subtracting that would tell me I have 8 moles of fluorine would be left over at that point. Yep. Now, mind you, if you happen to have done the limiting reagent calculation with the bottom one, you would actually need to go back and actually do this calculation to figure out how much is left over. So sometimes you get lucky, depending on which one you choose, that it happens to be the excess reagent. You can kind of do that calculation really quick, but other times you may have to go back and kind of do the calculation at the end to help you figure that out. Other questions on that? Okay, so let's take a look at one here in action, I think. Okay, so we'll go through this one together here just to see how it all works. So 6.83 grams of iron are allowed to react with 9.34 grams of sulfur. We want to know which of the two is the limiting reagent, and we also want to know how much iron 2 sulfide is going to be produced. So the first thing that I would do when I look at this problem is I see I have grams of iron, and I see I have grams of sulfur, and I know once I have grams of something, I could get to moles, and both of those things are the reactants. So I pretty much have enough information to get to moles of each reactant. That automatically tells me I am in a limiting reagent type of problem, which again means somewhere along the way, I need to figure out which one is the limiting reagent. By the way, they're not all nice like this and say, hey, find the limiting reagent, right? So these are the things that you want to look at. So again, we're just going to really follow the same steps as we kind of did previously. We are going to balance the equation, which looks like it is here in this particular case. We then want to convert what they gave us into moles. So we'll start with the iron, which is 6.83 grams of iron. Going to the periodic table there should be 5585, I think still. 5585. Again, the grams would cancel, and that would get us 0.1223 moles of iron. We'll do the same calculation for the sulfur, which is 9.34 grams of sulfur. Getting the molar mass from the periodic table, 3207 grams per mole, gives us 0.291 2 moles of sulfur. Again, it's important to remember these are your starting amounts of each of these guys. Any questions so far? Now, a very common mistake people will make is they'll look at those 2 numbers and go, well, it's the smallest one. It should be the limiting reagent, and that is not correct. It does happen a lot of times, but it is not the correct way, obviously, to determine it. So because it happens to be a limiting reagent problem, we are going to do that calculation. So what I'm going to do is take, if I want to figure out how many moles of sulfur I need, moles of sulfur needed, I'm going to take the moles of iron that I'm starting with, and I want to do a calculation to figure out how many moles of sulfur I need to put in there. From the equation, it is a 1-to-1 relationship between those two. So 1 mole of iron gives us 1 mole of sulfur, and that means 1 mole of iron on the bottom and 1 mole of sulfur up on top. They cancel. Tells me I need 0.1223 moles of sulfur is needed. At this point, I want to take this number and compare it to the number of sulfur I'm starting with. And do I have enough when I compare those two? So when I compare this number to this number, I do have enough, right? I only need 0.122 and I got about 0.29. So I have enough, which means the sulfur is the excess reagent. And by default, it means that the iron is the limiting reagent. Any questions on that part? Now, once I have determined that the iron is the limiting reagent, now I could actually go back to kind of the stoichiometry part and do step number 3. I'm going to use the starting amount of my limiting reagent, which is 0.1223. I am now going to do the relationship between the iron, which is the limiting reagent, and my iron 2 sulfide, which is what we're trying to find, which also happens to be, makes the math easy, 1 mole of iron is 1 mole of iron 2 sulfide from the equation. So we will do that. And again, the moles of iron will cancel, giving us 0.1223 moles of iron 2 sulfide. That technically would be our theoretical yield in moles. But in this case, I believe we wanted how many grams? So we need to do one more conversion here, which is use the molar mass of iron 2 sulfide. So using the molar mass for iron 2 sulfide, that is 5585 for iron and 3207 there for our sulfur, gets us 8792. And again, from the periodic table, obviously this comes from, times 0.1223 gives us about 10.8 grams of iron 2 sulfide would be produced, and again would be our theoretical yield here. So if we dump both of those grams into this reaction, everything went perfect, we should ideally get out about 10.8 grams of our product in this. Any question on those steps? So really the same sort of steps as a basic stoichiometry problem, with sort of the inserting of the which one is the limiting reagent problem at this point. Any questions on those? Now in this particular case, if I want to know how much excess reagents left over, what should I do? Which one's the excess reagent? It's the sulfur is the excess reagent, and we got 0.2912 moles that we started with. From our calculation down here, we figured out we needed 0.1223. So if we subtract those two numbers, right, that will tell me how many moles of the sulfur would be left over at this point. So again, that's a common question, sometimes asked how much of that excess reagent is left over. Any questions on that? All right, so I think we will lay it up there here.